All right, welcome back. We are Game 2005 in the fall 2022 semester at George Brown, and it's week 3 of our broadcast and recording together. And this week we have some internet issues, so I apologize. The laptops are probably not going to be able to connect, unless I'm wrong. Are you connected? So you're just playing around? All right, good for you. Anyways. Last we left off, we were talking about motion in one direction last week, and I know there was a super interesting talk about motion in one direction. You know, because physics and math is like, it's the stuff that you die for. It's not Cyberpunk Edge Runner. It's motion in one direction that we want to see this morning at 8 o'clock, right? And of course I lie because I'd rather watch Cyberpunk, right? Edge Runner and on Netflix and relax, but. Unfortunately, we have to go into this stuff, but there's some really great things because we're going to be talking about my good friend, right, Galileo, right? He's my good friend. I know, from a past life. He's one of these guys that develop things like, what if I throw a stone up in the sky? What happens? What's going to happen with that stone? Is it going to land? How long is it going to take? And but this is actually motion in one direction as well, because it doesn't matter whether you're going horizontally or vertically. That's why Galileo is included in this thing. If I'm not wrong, he was actually killed for his views on the heliocentric views of the universe, right? Which is like, we kind of went against the church's, doctrine, which was that the Earth was the center of the universe, right? And he's like, no, it's the sun, right? And obviously, that was wrong too. But back in the day, that's what we saw. We saw a few of the stars. And he started making these predictions. And you have to kind of praise these philosophers because they had very little data to go on. Their instrumentation was primitive, right? By the way, they're going to say that about us at some point in the future. They're going to look back and they go, remember those damn things they had in front of them? Laptops. And that little plate that they carried in their pockets? Phones, right? Why were they doing that kind of stuff back then? What were they thinking, right? Primitives. And it's like the same thing we look back now. We look back and we look at these philosophers and we're like, how do these guys figure this stuff out? How do these guys think about, motion in one direction? And they're thinking, we want to make, this is what I want to dedicate my life to. I want to dedicate my life to this idea of I can throw a stone up and how long is it going to take to come down, right? And start doing calculations. So that's what he talked about. He really talked about the laws of motion. And before Newton, it was Galileo. Right, so he was, he had quite an influence, and he wasn't just an astronomer. He did a bunch of other stuff with math and different things like that. And he talked about free fall. He also, he discussed terminal velocity actually back then. It wasn't called terminal velocity, but he talked about it. Does anyone know what terminal velocity is? Yeah. Yes.
It's the maximum speed at which you can fall where the force of gravity is in equilibrium with the drag from the earth.
Wow, that's a pretty good one. You did good. You did good. So the answer was, I'm going to paraphrase, it says, it's the maximum velocity of an object, any object that's falling, that's, kind of goes into equilibrium with the air friction, right? Because basically an object's going to fall at a certain speed. And then the air friction is going to cause resistance, right? And the resistance is going to buoy the object up. Buoyancy, like when you float on water and stuff like that, has the same principle, right? So the water pressure is something that's going to basically push a boat up, and it kind of works the same way with planes and with objects that are falling, right? There's some kind of air friction that kind of pushes it up. For us, for our physics as game devs, we're not going to care about air friction, typically. Unless you're going to do some kind of wacky simulation or something like that. We don't care about those things. We kind of say, all things being equal, let's assume that the friction is 0, right? Because it becomes a very challenging calculation. Unless you're making some kind of game like that where you're like, hey, friction. It's like, let's turn up the friction somehow. I don't know. I haven't seen a game like that, but let's suppose you had something like that. But what is terminal velocity? Does anyone know approximate speed? Well, let's say, for a human. 200 kilometers an hour, approximately. Yeah, it's around that, 150 or 200. It's pretty fast. Anyway, you're still going to break every bone in your body if you're falling that fast, right? I mean, unless you're lucky. People have fallen from planes and somehow lived, no bones broken. I don't know. For me, that's not my karma. I would probably break everything. But falling objects, we got to talk about this. So there's three types of things that we can look at when it comes to falling objects. Again, this is continuing motion in one direction, just on the vertical instead of the horizontal. Three types of falling objects: dropped. So I drop an object. Galileo, he's like, let's drop an object, see what happens. Right? Thrown down, so I take some energy and throw it down, right? So add velocity. Or thrown upwards, what happens? And he started to observe some patterns. A lot of this happens because of gravity. There's a lot of symmetry that happens because of gravity, believe it or not. We have parabolic motion because of gravity. And so the same thing we're going to see here in when we throw objects up or thrown downward. So when it comes to a free-falling object accelerating, he basically calculated, he started figuring out how long it takes and how fast an object accelerates. And I'm not going to give him credit for figuring out that our gravity is approximately 9.8 meters per second squared, but he did come close to that approximation. So he called them G's usually, or G-force a lot of times. So the force of gravity, or G, right, is negative. It's usually in the negative direction because it's going downward. So we're going to look at a number line for gravity, where positive is up and negative is down, with respect to let's say the surface, wherever that surface is. Then it goes about 9.8 meters per second. Now, question for you guys: you're making a platformer. We've talked about this before. Should you make gravity in your platformer in Unity or some other game engine 9.8 meters per second? People are shaking their head. Why not? I mean, it's the force of gravity. Yeah. Too floating. You said that a couple of times. It is. It's too floating, right? It doesn't look right. Why? Why does it not look right? We're talking game dev now. We're not talking about like physics for a second. But let's just go to the game dev world for 1 second. Right? Yeah. Quick and snappy. We said that too. I said that too. Quick and snappy. Right? But why? Why just quick and snappy 9.8? If I jump up right now, I'm going to be quick and snappy, fall down on my head, right? So. And I'm not Mario. I can't jump up and down like he does. So I talk to my wife. Why?
I was just going to say, we can't jump like freaking 5 meters in the air.
We can't jump 5 meters in the air. But even if we could, right? I mean, it would look pretty snappy for us. It'd be like, a lot of times it has to do with scale, right? And this is something that we have to talk about from a physics perspective. How many pixels per meter, right? That we're going to start talking about again. I want to take my my coordinate space. Right, my addressable space. By the way, our addressable space we're talking about right now is 2D, so X and Y coordinates. The addressable space that we use in a 3D game, X, Y, and Z coordinates. One day, the addressable space that we're going to see through our lenses, right, which is all of this, right, in real time. Right, we're going to see everything as addressable space. We're going to be able to put, in my opinion, I'm not a futurist, but if I was going to predict, right, what we can do in the future with things like XR, fill in the blank, whatever that's going to be in the future, where things that are unobtrusive are addressable space to compute in the real world, right? Where we can put objects in the real world, and we're going to be able to see them, we're going to be able to label them for whatever reason, right? We're going to bring objects that are virtual into the real world, right? And it's going to help us do a lot of different things that we can't even fathom today, right? Like I said, we're going to laugh at ourselves and say, remember that laptop we used to have? Right? Seriously, we're going to do that. Because just like I did when we look at the past, the 1970s, we see these like, Ryler, which was a big computer, 4K. It's got less memory than, the space shuttle, right? And all that kind of stuff that was out there. So we digress, but the thing is, addressable space. When we're looking at addressable space, we're trying to think about how do I partition, how do I create a division scheme for addressable space so I can, create a physics simulation. Right? Even if it's for a game, I need to be able to partition it. So I'm like, how many pixels am I going to allocate per meter? Is it 30? Is that the number? Right? Is it 40? What is it? I have to come up with something. And so one of the things that you should start thinking about is, I'm doing my physics simulation, is that I have to have a ppm, a pixels per meter, right, calculation. Once I get that pixels per meter, then I can start applying 9.8 meters per second. 9.8 times whatever that ppm is, right? Per second, right? Wait a minute, per second. This is another reason why it's floating. We talked about floating. Per second. We're not doing per second, we're doing per frame, right? That's another really weird thing. Should we be doing it per frame? Because that's also wrong in some ways, right? Because per frame is one slice of a second, right? So that's something else that we have to figure out. And so these adjustments that we can make, and you can actually see it nicely in whether you're using Unity or Unreal or our own little game engine for the assignment framework, it doesn't matter. That's the thing that's going to make a difference. So that's where 9.8 can actually look okay, right? Start adjusting your pixels per meter. Start adjusting your frame rate. You know, the amount of seconds that you do your calculations, and then you'll see a difference in the way things work. So again, 9.8 isn't a bad number. It just may not be the number that we use in game dev. Like we said earlier, we're going to neglect error resistance. And the reason why is because it becomes a very, or sorry, not very, but much more complicated calculation, right? What we want to do is we want to have consistent or constant acceleration, right? Once we bring error resistance in, the faster we go, the more error resistance there is. And it's not constant. It really depends on the shape of your object. So, again, if I take two objects, one object that's shaped like a stone, and another object that's shaped like a feather, and let's say the feather and the stone for, I don't know how, well, let's suppose these things weigh the exact same amount, right? The feather is still not going to come down the same speed as a stone because of the shape, right? Because what's going to happen is as we flatten it out and I increase the amount of area that I'm applying against force, whether it's water or this fluid that we live in, because we live in a fluid, right? Even though it's air, it's a different type of fluid. We just can't perceive it because we live in it, right? I'm thinking about some fluid space now, I don't know why, Star Trek. Anyways, but if you think of fluidic space, but if you think about this, right, and you have this air resistance, so you have this feather that's pushing down on the air resistance, it's a larger area, and so because the area is spread out, it's going to, kind of seem or appear to be moving slower than a stone, because a stone is not going to have any buoyancy, it's just going to go straight down, right? So same weight relative to the Earth, different speeds when it comes to falling, and that's why we can't, as game devs, think about these things, because it's like, how does that make any sense? Why do we even care about it, right? Because we don't. Not when it comes to gravity, typically. So that's one thing we want to say. We also want to think about, from a kinematic equation perspective, that displacement is in the vertical direction. Okay. We were talking about displacement, and last week we had this conversation about the difference between distance and displacement, which is going to be on your test. What is the difference between displacement and distance? We talked about this really briefly, and I'm going to see if I can access this part of the room here, because this part of the room here is always... Yes? How far you are from the starting point is displacement. Yeah. Distance is? How far I travel. Okay. Well, is there another way we can express that? Same idea. Can we express it in different terms? Some other person. Anybody. I don't want to keep looking over here because I'm going to bother you, and I don't want to do that. How about my friend Marco? Okay, so displacement and distance. We know that displacement is different than distance. Let me come back to Karen. Tell me how do we express it differently? Try again. Try, one of our friends here. Yeah, difference between displacement and distance. Distance is A. Scalar? Okay, that's another way, Karen. You want to say that? Okay. How about my friend over there? Displacement and distance. Displacement is distance from the ocean. Okay. We don't want to put displacement in terms of distance when we talk about it. I would rather say something like this, okay? When we think about, okay, we have someone else. Go ahead.
I was going to say one has a direction.
One has a direction, and the other one?
It could be going in any direction if it measures how far something is.
I always think about distance as path length, right? So I kind of think about myself when I think about, an example of distance compared to displacement. Remember we had that kind of a squirrely path, and it came from A to B, right? But then we can draw a line as the crow flies from A to B, right? That's what I want you to think about. As the crow flies, if I was able to fly, in a spaceship from A to B, let's say from your home to here, right? It'd be different than the path you took to get here with your car, right? Or by transit, or however you got here, right? The path you took is the distance as the crow flies. If I was going to take, I don't know, some, futuristic drone technology, it would get into this drone car, fly to your house, whatever it is, right? That's the displacement from there to here, right? It's like a direct line. And I want you guys to think of it that way because that's what we do. If I said, we're looking at it from addressable space again. I'm looking at X and Y coordinates. I'm not looking at like a path to get to that place, right? And it makes a huge difference. So displacement in this case means we don't care about lateral displacement. We don't care about X and Y. X. We care only about Y in this case when we're dropping stuff. Okay? Which is, when you think about it, before I move on, when we start thinking about motion in two directions, which is going to come next week, right? We kind of decompose the vector, right? We decouple each of its components, X and Y, and we start thinking about it in terms of, okay, I'm going to go X is on the horizontal and Y is on the vertical. I want to decouple these two things. And once you start doing that, for that kind of stuff, that's when you can make your kinematic equations, you can solve those things a little easier. And we're going to be doing those kind of examples next week. So one thing to note is, here's case one, okay? So I take an object, I'm going to drop it as an example, and we want to set a couple of things. One, the initial velocity, if I hold a rock or some kind of ball or an object in my hand and then just let it go, the initial velocity is 0, so there's no velocity, right? I also wanted to say that we're going to set up a number line. We're going to set up a measurement system. Remember, what we always want to do is try to apply some kind of measurement or division scheme. It doesn't matter whether we're trying to figure out collision detection. We want to divide up the world, right? That's what game developers do. Actually, that's what physicists do too. We sit there and say, okay, how am I going to create a bounding area for this thing? I'm going to create a bounding area for my world, right? And that's what I'm doing here too. The division scheme that we're looking at is up must be positive, down must be negative. And then we're going to use the kinematic equation to figure out and we're going to flip X for Y in this case. We've been doing things across the X-axis with, cars accelerating and decelerating last week. Today we're going to talk about the Y-axis, still motion in one direction. Okay? So we can say that the acceleration across the Y-axis then is a negative g, right? Because we're going in the negative direction, so it's negative 9.8 meters per second squared, right? And that's also something else we have to keep in mind. It's per second, right? So that's also something that's different than what we're looking at. Initial velocity, again, where it's not equal to 0, or with upward being positive, initial velocity would be negative, right? So it's going to start off that, the initial velocity is going to start going down. And another thing we know, if I take an object, so case 2, and I throw an object upward, right? So again, the initial velocity is upward, so it must be positive. That's one thing we also know. So this is case number 2. And the instantaneous velocity at the maximum height is 0. It's almost like our object tends to hang in the air for 1 second, or not even a second, a fraction of a second, and then a moment, let's just call it, and then it starts to fall back down. And it kind of slows down. It slows down, until it comes to the top, and then kind of falls, right? That's what happens. One thing we know is this motion is symmetrical, right? And in fact, one thing we also know, we're going to see in a second, is the velocity that we send an object up with is the same velocity that we get when it comes down, which is kind of interesting. So if I throw it up at 20 meters per second, right? Then when it comes back down, it's going to come back down to me in the same place at 20 meters per second. When it goes lower, it's going to keep going faster and faster. Right? So if I'm sitting on top of standing on top of a building, which is kind of a classic scenario when we talk about this thing. I'm on top of a building, the rooftop, throw a rock up in the sky or whatever, right? It's going to come down to me the same acceleration rate or the same velocity as I threw it up with, and then it's going to gather speed as it goes down, right? And that's kind of a problem we have to solve. You might see that on test intent. It might be a test problem, right? A test thing. In fact, everything you see on the PowerPoints that I shared with you are good examples of test questions you might see on your test in week 7. All right, so again, we know that the motion is symmetrical, right? And it says maybe, but again, all things being equal, where when we generally assume that friction is 0 and all that kind of stuff. So here's the free fall example, and I want to talk about this. And this is the classic example that we're talking about. I'm going to zoom in here so we can see it a little bit more clearly, because I know we don't have any internet access. So bear with me while I try and do this with one hand. It's not going to happen. All right. Okay, so what we see here, if you look, is you have a person and they're throwing an object up into the air, right? But they're on top of a building. And this is the exact scenario that we talked about, right? So we start setting up our variables. And these are our initial conditions, all right? So time is 0, right? We know that that is true. Time at position A, this is the position A is 0. The y, we kind of consider this area here as the 0 point, if you will, right? And then velocity across the y-axis, right? Again, we're throwing it up with a velocity, and it's a positive number because it's going upwards at 20 meters per second, right? And then gravity, the acceleration due to gravity across the y-axis is minus 9.8 meters per second squared, right? So then when we throw it up, we can make the calculation that by the time it gets to B, the time it takes is 2.04 seconds, and the total distance across the y-axis is 20.4 meters. All right, so distance here is 0, distance there is 20.4 meters. And then as it comes down, velocity across the y-axis at this point is 0, so it's not going upwards or downwards, it's kind of hanging for a second for this moment. And the acceleration due to gravity maintains is the same. And here's the symmetrical part. Take a look. If it took 2.04 seconds to come up, it's going to take 2.04 seconds to come down, which means that the total time it'll take is 4.08 seconds. And this is a key learning when it comes to throwing objects that Galileo figured out. Symmetrical motion, right? Time it takes to come up, comes down, or, which is the common saying, which is whatever goes up must come down, right? He came up with that, believe it or not, in one form or another. So that's pretty cool. But it continues, and if you notice, the motion continues, and this is the non-symmetrical part. The non-symmetrical part is when it leaves the area that the observer, kind of threw the rock and came down. It's going to continue going down, and it's going to continue to gather speed because of the acceleration due to gravity until it hits the ground. And when it hits the ground, because the building height, or the height from the ground level to where the person threw the object, as an example, is 50 meters. Notice it's not the top of the building, but actually his hand, or their hand, right? That's where it's measured as 50 meters. That's really convenient for us. It's not like 48 point something or whatever his height is. And you might be given something like that, where you have, here's the height of the building. The height of the building is 45 meters, and the man or the person is 2 meters tall, right? And then, if they're throwing a rock, they've given you this information. And usually if they're giving you this information in a question, you should take that into account. The man's hand is 2 meters above the roof of a building or something. Now you know that the total height is 47 meters when you start doing your calculation, right? So then it will fall if it comes from here. And if this is 50 meters in this case, it's going to continue to fall down for another 50 meters, right? So when it falls for 50 meters, we can start doing that calculation. How long is it going to gather speed? And how long does it actually take to come all the way down here? And this is total time, by the way. So the total time traveled from his hand all the way down to the ground here, minus 50 meters from the origin point, right, is 5.83 seconds. So total displacement is, remember displacement and distance? What's the total displacement from his hand? Total displacement. Yeah. How much? Say it again? Negative 50, thank you, right? That's all right, but we have to take into that account because remember displacement is either positive or negative, which means it started below where it began, right? Or downwards from where it began. So keep that in mind because you might get a test question like this, and the test question will say 50 minus 50, yeah.
So what's the difference between the y and the y?
It's the velocity across the y-axis, and y is the total distance. The displacement, sorry, yes.
So why can it be positive or negative? There's no point of reference.
There is a point of reference, his hand. Remember we said in the upwards direction is positive. When we started to divide the, our world, we said that the y is positive from his hand up, and anything down below his hand is negative. That's what we came up with, right? So the questions will tell you those things, yes. Yes, there will be equations. Yeah. So, but you're gonna have this open. Don't worry, right? I don't think we're worried. Open internet and open book, and you have access to everything. 2 attempts. All right. So it's not like you're gonna. I'm not trying to stress you here. It's not about that. And I'm going to give you a cheat sheet. Chances are too. All right. So don't worry. Huh? Well, look, guys. I don't expect you guys to remember anything. Right, truly, I really don't. Look, do we really remember anything when we code? No. I'll look it up. If I have a problem, if I don't know how to do something. I mean, look, how many languages do you code in right now? 2? 3? I'm saying? Over the time that you're going to be a developer, you're going to be, coding whatever language you need to code, right? So, are you going to remember the nuances of every goddamn language you're coding in? No, you won't, right? And chances are the languages will keep evolving, so you need to reference them, and it's okay. No one's going to, unless you're in an interview and you're doing something like a lead code, test or something like that, which is, in my opinion, ridiculous. It's the silliest thing ever. I agree with that, right? No one's going to expect you to know these things. No one, right? They're going to look at your process, your thinking, right, when it comes to this kind of stuff. And that's what I want. When I'm looking at your code or when you're doing a video or something for an assignment, we'll talk about an assignment in a second. All I care about is what are they thinking? What was the process? What was the outcome? Did they get the outcome that they thought they were going to get? And why is it that they got this? That they have this problem? Then we can make corrections if we need to. So this is it. So the initial velocity at A is upward. At B, the velocity is 0. At C, the velocity has the same magnitude as A, but in the opposite direction. And then the displacement is minus 50 meters because it ends up 50 meters below its starting point, okay? So that's almost like if we were going to put it on a number line horizontally, it would start 50 meters behind the person where they started as opposed to in front of. So when we think about this, and I'm sorry, back to the sentiment. I'm talking about equations at 8 o'clock in the morning. And people are squinting and they're going, why am I looking at this thing, right? So once upon a time, before calculus, right, we were trying to figure out, someone smart was thinking, I want to find the area under a curve. And how do I do this thing, right? Without math, what can we do? We can take rectangles and we can start kind of slicing up the area under a curve with smaller and smaller rectangles, very, very small, right? And as we do, if you try and do this, try it for yourself, right? Actually, if you want to try, so draw a curve and then start, actually measuring. So it's kind of a very monotonous exercise, but really meticulous as well, right? And you're just going to start drawing these rectangles over and over again. And you know the size of the rectangle, so you can actually figure out the area of a rectangle, which is times width, right? And then you add up all the lengths and widths, like the areas of all the rectangles, and you'll get a very close approximation to the area under a curve. That is how we used to do it, like rough. You can still do this today. If you really want to find the area in a specific area, the area that's irregular, like this, you can kind of partition. We were talking about division schemes, the same idea. I'm dividing something as much as I can into things that I know, right? And then I'm approximating what it's going to be. I'm going to be off. We're always off, right, with something. Common saying, models right? If I make a model of the universe, models are always wrong, right? Models are always wrong because it's just a model. We don't know anything, right? We're assuming, we're making assumptions, we're making hypotheses, all these things. But models are always wrong every single time, right? Oh, we're close. We can make approximations. We can, we at least have an idea of how the universe works. And so too, this is the same way. So before we had calculus, we used to use these, integrals, right? We used to have, we wanted to integrate all of the, rectangular calculations under the area under the curve to figure out the area under the curve. And then we came up with some ways of trying to figure it out. So here, when we look at the area under the curve here, we're looking at it saying that t initial, that's time, right? T final on the other side here, right? And the displacement equals the area under the curve, and it's the velocity time curve, right? So as my velocity changes, and you can see that the velocity is on the y-axis here. So on the left, that's velocity across the one axis, right? And then on the bottom axis is time, right? So if I was going to look at this, and this is a motion curve again, I know I was telling you Josh loves motion curves. So if you haven't seen that already, we didn't talk about motion curves yet. If he hasn't, we will, all right? Because he loves motion curves. This guy Josh, my good friend. So, so what we want to do is we want to find the integral. I want to take all the little time slices, all the slices under the curve, right? From ti, which is the time initial, to time final. That's what I want to do. And the delta t, depending on the instantaneous, kind of part. If I was going to look at a specific spot on the curve, right? That's the delta t, the time between ticks of the clock, if you will, right? Which, by the way, going back to what we said last week, Einsteinian motion. Remember, I digress, but I'm going to say this because it's interesting. As we approach the speed of light in a vacuum, remember what I said, right? What happens to the time between ticks on the clock? What happens to those things? So the time ticks, tick, tick, normally, right? But as we approach the speed of light, what happens? Does it slow down or speed up? For the person that's riding, if I was in a spaceship and I'm approaching the speed of light, does it get faster or slower for me? And what about for the people, the observer outside of the spaceship? Normal, right? But for the person inside, they're actually time traveling, right? And it's almost like they stop aging, right, in some ways. That's the Einsteinian theory, right? So here we have time between ticks on the clock too. But it's almost like, t initial to t final. And this little time slice that they've highlighted here is that one part of the area under the curve that we're looking at, and different parts. And that tells us almost like the instantaneous displacement, if you will. So we have some equations, and I'm just going to show you these things in calculus form. Just 1 second. Remember, what we want to do with calculus is we want to do two things a lot of times. We want to take the derivative. I want to derive one formula from another, right? And again, I talked about this, and I'm only talking about very simply because remember that motion graph I showed last day, which we had position, velocity, and acceleration. And they're all in one graph, okay? That's a key thing to look at because we can derive one, kind of motion from another one. If I have position and I have my position equation, I can derive velocity. From velocity, I can derive acceleration. And it's the first or second derivative. That's what we call it in calculus. At the same time, I can go back the other way, right, and say, if I have acceleration, then I can figure out what my velocity is. We can get the integral of acceleration to get velocity, and the integral of velocity would be displacement, that position, right? So this is kind of what this is showing you here. And you can identify certain things that you might be able to see. For example, we know velocity on the x-axis final minus velocity on the x-axis initial is equal to integral from time 0 to time t, where t is infinite, right? Times the acceleration across the x-axis dt, so relative to change in time. Again, I'm just showing you these things just so you understand that there's always a calculus version of the equations that we showed you, with our kinematic equations. So when let's start thinking about this, right? Calculus is the way we can derive other kinds of equations. So here, it's talking about how using integrals, we can figure out that, and converting it back to non-calculus equations here, this is kind of a key equation. So the velocity on the x-axis final minus the velocity on the x-axis initial is equal to the acceleration across the x-axis times time, right? And this idea, once we move things around, right, again, where we sub in x final minus x initial, right, we can derive an equation that looks like this. And this equation, when you look at it, it looks complex, right? But actually, this is our parabolic equation. This is the equation of equations, if you will, for what we want to use. And we're going to see it in another form next week, except we're going to be doing motion in two directions, right? And here's an example of that. So x final minus x initial is the total displacement. So if I'm looking at, like, what's the total distance that I'm going to go, or the total displacement, that's the stuff on the left. And then vxit is velocity on the x-axis times time, right? And then plus 1/2 at squared, right? Once I have this equation, and if I move over the x initial over to the other side, so I take this x initial, remember whenever we move something from the left side, algebra, to the right side, then the sign flips, right? So then really what the equation is, x final is equal to x initial. And we can also say position initial, right, which is p naught, and sometimes we say p naught, and then is not 0, right, the initial position. And so the initial position plus the initial velocity times time plus 1/2 at squared. And that's the thing that we want to use. If I take this information and if I apply it to Galileo's, throwing a rock up in the sky, will it work, is the question, right? Well, let's think about this. If we think about the equation, let's just look at it, do a little bit of a mind, let's calculate stuff in our mind for a second and see if it works, okay? If our initial position is 0, right, then we can eliminate the xi term because the initial position is 0, right? We don't care about the initial position, right? We want to find the final position from the initial position. We start off at 0. And if I was to, throw a rock up into the sky, the initial velocity is 20 meters per second, right? So 20 meters per second. We know that the acceleration due to gravity is negative 9.8 meters per second, but we're, kind of dividing that by 2, so it's negative 4.8 or 4.9, whatever it is, right? Negative 4.9. And now we're calculating time, and I want to say, let's plug in the time values that we were given. We were given time values, right? We can derive the total displacement if we have the time value, right? Does anyone want to try this equation out? You're looking at it going like, I have 2 heads, right? I'm telling you, if you do this, right? Or if we did it the other way around, if I say that the total displacement, we know that when I throw a rock up into the air, the total displacement is going to be minus 50. Now we have another value, minus 50 over here on the left-hand side, right? And if I took minus 50, right, and I plugged in, we know the velocity, we know the acceleration, and now we're trying to figure out the time, right? Because I have that, t squared, I need to use the quadratic equation, right? Minus b plus or minus the square root of, b squared minus 4ac over 2a, that quadratic equation. Don't worry, you don't have to remember it. Once I do that, I can figure out time, right? And that time is something I can plug back in to verify, what I'm doing, right? So in this case, we have all the numbers, and the equation should be in equilibrium. It should be in balance. If I put minus 50 here and I plug in the total time in seconds that they gave us, 5.0, whatever it's going to be, it should be very, very close. Try it yourself, all right? So what I'm saying is, if you go back up to this little drawing, right, and you look at the total time at the bottom, 5.83 seconds, right? If I take that 5.83 seconds and plug it into t, right, so I put that in there, right, 5.83 times velocity of 20 meters per second, right, that's where we start off. Let's do the calculation. Come on. And I'm going to go off mic for a second while I type. I'm sorry. So again, what you want to do is you want to start setting up your equation. I put the S in here so that way I don't lose my place when I start typing the equation in here, right? So if I start typing it in, it's going to be this. I know that it's minus 50. I know that that's on the left, right? And I know that's going to be equal to velocity xi. We don't care about the negative xi because we know xi is equal to 0. We know that, right? So we can eliminate that because that's the initial position. It's 0. It's at my hand, right? So then what I can do is I can sub in the numbers that I know. So I know this is 20 meters per second, and I know the total time is 5.83 seconds. I know that those are the things that I know, right? Plus 1/2 AT squared, which is a negative, let's put that in, 4.9, right, is what's going to be there, times t squared, which is 5.83, right, all to the power of 2, right? So something like this. And that's the equation, really, when you think about it, right? So that's the first form of the equation, if I was going to think about that. That's me subbing in the numbers, all right? And then what I want to do is, and again, let's see if we can do the same thing for the next part. And then what I do is want to solve some stuff, right? So again, it's going to be minus 50, and then let's do that calculation. What is 20 times 5.83 to be exact? So calc. So 20 times 5.83, right? So now we're looking at 116.6, just to show you how this works. 116.6. Okay, I lost that one. That's fine. And then plus this part. Now this is more tricky to do. Remember, from an order of operations perspective, you want to do this 5.83 squared first. So you calculate that first. So 5.83 squared. If I can actually use my thing without touching the pad here, times 5.83. So we're looking at 33.9889. So 33.9889, right? And multiply by a negative 4.9, right? So that's what it was there in front. Okay, so 4.9. So that's the next step that I would do if it was me, okay? And I'm sorry I lost the equation. We can just, install it there again. I can just go here and go equation. So because it kind of looks the same as the other one. Actually, it kind of made it worse. There we go. So then the next part is we want to continue with this idea, this stuff where we say minus 50. All we want to see is if it balances, if the equation balances, right? So let's do the next part. I'm going to still keep 116.6, and I'm going to multiply minus 4.9 times 33.9889. So multiply by 4.9. Flip the signs, which is minus 166.54561. Minus 166. Right? So that is minus 166. What is it? 0.54561. 0.54561. That's what we have. And now we can see that a negative actually becomes a negative here, right? If we start thinking about this, let's see if we're close, if it balances, or if I made a mistake, right? So now we're going to say that minus 166.54561, right? Plus 116.6 plus 116.6 is approximately 50. Right? We're losing stuff because our seconds weren't accurate. They gave us a rounded off second number, and that's why we're getting that discrepancy. So you can clearly see that it equates. Both sides are roughly the same amount, all right? And that's how we figure it out. So why am I showing you this? Right? Why did I bother? Yes. Minus 50 is the total displacement. We know that these are all the knowns. We know that the total displacement is minus 50. We know that the total time it took in the diagram was 5.83 seconds, or whatever it was. We know the velocity that the experimenter, or whatever you want to call them, threw the rock up, or the object in whatever. We know all those things. We know gravity is negative 9.8 meters per second. We just plug them in under. Sorry, the xi? Xi is the initial position, which is, in this case, relative to the observer, the 0 point, where you started throwing the rock. Make sense? Yes.
So say we had a question like this during the test, would you be looking for the exact, like, say like you got the 49.94?
I probably would want to have at least three decimal points of precision, as close as possible. And again, you're going to choose the best answer. You're not going to give me the answer. You're going to choose one from the best one from the KGCP.
So, just to be clear, A is gravity.
A is gravity. Yeah, A is gravity. Acceleration. A is acceleration due to gravity. Acceleration due to gravity is the acceleration we have, and we're just plugging in the numbers. Okay. I'm doing this exercise with you to prove that this equation is a balanced equation, right? A balanced equation means anything on the left-hand side equals anything on the right-hand side. And that's how we were able to figure this out. We know that, x final is minus 50 meters of displacement because it's going to go down from the original location. And all we're doing is hoping, that's what I was hoping at the end, right? That the stuff on the right equated with the stuff on the left, and it did, yes.
So if x9 and I are the initial coefficient, then what is just x?
That's the total displacement. But that's like, if I was going to say, there is no just x, right, ever. It's usually x initial and x final.
I mean, you have a with an x right there.
A across the x-axis. Acceleration across the x-axis. Or acceleration across the y-axis. Or acceleration across any axis, z-axis. You can sum in the axis that you want. Remember, we're just talking about motion in one direction. Any other questions around this idea? Right? I'm showing you this because you should be able to test out any numbers that you're given. Right? If you have the answer, you should be able to check your answer. Yes. Why do we have to do what? Oh, that's part of the equation. So what they've derived is they've figured out that this equation, this kinematic equation, when they figured it out, they came up with this equation after several experiments. Right? They figured out that there's always 1/2 of gravity. Because of gravity being symmetrical, right? The symmetrical, tendency for things to go up and come down, right? Okay. So this is the idea behind that, and we're figured out that everything is in balance. This is good, and I'm just putting it out there so that you guys can see, why this equation works. Okay. We have to talk about this too, and I kind of talked about this last time where we said we have to start figuring out or developing a general problem-solving strategy, right? And what they recommend is we start with concept. Actually, we start with concept when we're making our games too. We start with concept. We start thinking about how things are going to work. We analyze, and then we finalize. And when we start categorizing, we say, so conceptualize for me means draw it out. If I give you a problem, do your best to draw the problem out, because then you can start understanding what the problem, how to apply yourself to the problem. The categorize part is like, what problem is this? Is this a problem where I'm throwing a rock up? Am I throwing a rock down? Am I dropping a rock? What am I doing here? Which one of the equations am I going to use against this problem? So that's the categorize part. And then the next part is start plugging in your numbers, analyze, right? And then figure out the answer, finalize, and make sure that it all balances, right? So this, these 4 steps of problem solving are the things that I recommend for when you do your test. So again, it talks about these exact things here. Just going to move on to the next part. Okay, some problems. Let's think about these problems, right? So a racing car starts from rest at t equals to 0, right? And reaches a final speed of v at time t, okay? If the acceleration of the car is constant during this time, which of the following statements are true? A, the car travels a distance of vt. B, the average speed of the car is v over 2. C, the magnitude of acceleration of the car is v over t, right? D, the velocity of the car remains constant. E, none of the statements, or the next one is A through D is true. Which one? So all of them except for the last one. Now you're given some information. Sometimes you get a problem like this, and you see a slice of road, and you're given 600 meters. Does that have anything to do with what we're asking you? Nope. A lot of times you get something like this, and it's almost like it obfuscates the problem. It kind of shades, it kind of puts it into you know, tries to hide it or tries to make the problem more difficult than it is. So it's at rest. So we start at rest. That's the one thing we know. The car is starting at rest. The next part is it reaches a final speed of v at time t, right? So what it's asking is if the acceleration of the car is constant. Remember that we only deal with constant accelerations right now, right? We haven't talked about acceleration that goes up and down, right? So if the acceleration is constant, then it says what's true. Can we say that the car travels at a distance of vt? We have to look at the kinematic equations for this, you know, from last day to figure out which kinematic equation applies to this problem, right? So again, when we look at this, you know, conceptualize. Which ones am I going to use? I can picture my car, I might draw the car on the road. And then second one is categorize. What equations that I need? I need acceleration in my equation because we talked about acceleration here. I need time because we talked about time. I need velocity and I need this displacement. I'm thinking of all those things, right? I don't have parabolic motion, so it's probably not going to be x final is equal to x initial plus, you know, vt plus 1/2 at squared. Probably not, right? Because that doesn't make any sense, right? So those are the things that we have to think about. V is 0 at the beginning, so v naught t, initial velocity is 0, right? We start off with initial velocity 0. We can cancel out that first term. So it's really VAT that we care about, right? So which one of these things is true? Car travels at vt, the average speed of the car is v over 2, you know, and so on. And that's the kind of stuff that you're going to be asked. This is a question that is, there's no numbers around. You've got to select which of the answers is true. And you've got to compare it against the equations that are out there. Okay, let's actually get some numbers. So this is what they actually, this is the solution to this. So the initial velocity of the car is v naught is 0, and the velocity at time t is v, right? And the constant acceleration, therefore, is given at, the acceleration is the change in velocity, or the change in time. And we can break it down, so we can see that it's v over t, right? Just going from one side to the other. So again, it's pretty simple. What these guys did was said, okay, so what is acceleration anyway, right? It's the rate of change of velocity over the rate of change of time. So as we take the velocity time graph to figure out acceleration, we can figure it out. And if we break down what velocity the delta v is, delta means change in velocity. So we can say that the velocity final minus the velocity initial over the time final minus the time initial. And we plug in some values, and we know that velocity initial is 0, time initial is 0. So really, it turns out to be v over t. That solves one of the problems. So one of those questions is correct. So we know that the car travels a distance. If I go here where it says v over t, so c is okay, right? C is okay. What else do we know? The average velocity of the car, because it asks what's the average velocity of the car. The average velocity of the car is, v initial v final plus v initial over 2, right? And we know that v initial is 0, so we know that eventually it's going to equate to v over 2. So that's also correct, right? Because we said that the average velocity is v over 2, right? And they keep on breaking down the statements. So it says only statements B and C are true. Those at the end, right? And some of the other ones are not true, right? Because A is not true, and they disprove it here because they're just using basic, some of the basic equations. Delta. So whenever we see delta, what does delta mean in Greek? Change, right? So whenever you push anything to GitHub, it says calculating deltas, right? If you ever look at that, that's kind of part of your GitHub stuff, right? If you're trying to do an actual physical push, like, by hand through your console, right, or your terminal. It's calculating deltas, which means it's calculating the changes, right, between your initial snapshot and what you're pushing, right? So deltas are used everywhere else, right? It's used in math, it's used in business, it's used in physics, right? We want the deltas. A lot of times, when I was in industry, a lot of times they would always say something like, give me this, talk to me about the deltas here. It was like, these buzz terms, industry buzz terms, I would say. We have a lot of those. All right, let's continue to go back to this. Problem number 2. Let's see if we can figure this together again. The position versus time for a certain particle we know it's a particle, moving along the x-axis is shown in figure P2.1. Find the average velocity in the time intervals A, 0 to 2 seconds, B, 0 to 4 seconds, and C, 2 seconds to 4 seconds, D, 4 seconds to 7 seconds, and E, 0 seconds to 8 seconds. So it says, find the average velocity. How do I find the average velocity? We just did it. I take velocity final minus velocity initial, right, divided by 2. All right, so it says between A, 0 to 2 seconds. So here's 0, right, and here's 2 seconds. What's my final velocity? 10. What's my initial velocity? 0. 10 divided by 2 is 5. So the first one is 5 meters per second. That's the average velocity. And then you can do it for every one of those intervals. Yes?
So if you have 3, you have to take the average of 3 and just be divided by 3.
3. Each of the intervals, right? You just take all those intervals and divide it by 3, right? And actually, they show you that here in the solution. So here's the solution for that, for each one of those, right? So again, I'm sharing this with you because these are templates for potential questions you might get on the test, right? That's why I'm giving these to you. So that way, if you see it, you're like, I saw something like that in Tom's lecture. It's in the back of the PowerPoint slides. Hint, hint, some of the questions you'll get will be eerily similar to these ones, all right? So you know where to look when you want to kind of try and figure out some of these things, right? And you might get some of your marks in these things as well, right? So here we have the stuff, we said 5, and then, so x is 50, 5 meters at 4, at t is equal to 4, right? So we take 5 meters minus 0, 5 over 4, 1.2 meters per second, and so on. And then you can find out the total, for the average. Now this was interesting because from 0 to 0, right? Why do we say from 0 to 0? Because the total displacement at the end of the day, when we go from 0 to 8 seconds, right? What's the total displacement? Again, this is the tricky part that you might get fooled about. Some people do this and they're trying to calculate this as a path. What's the displacement from the 0 mark? From 0 seconds to 8 seconds. The total displacement is 0. 0 divided by 2 is 0. You have 0 average speed, right? Because the average velocity is the total, velocity is a scale, vector, not a scalar, right? So if we divide, we don't have any velocity here because velocity is based on displacement, not distance, and therefore the average velocity would be 0. From 0 to 8. And that's the tricky part. When you look at it, you're like, you might get that one wrong, right? Because you're like, you might try and do some weird calculations. Some people do weird stuff. I've seen this on the test where they actually hand-coded stuff when they handed it in. And they said, so I calculated this interval, and I calculated this interval, this interval, this interval, and this interval, and I got this. And it's completely wrong, right? Because it's not the point, right? Okay, a couple more. Problem. A person walks first at a constant speed of 5 meters per second along a straight line from point A to point B, and then back along the line from point B to point A at a constant speed of 3 meters per second. What is her average speed over the entire trip? Okay. So 5 meters per second you walk from A to B, when you walk back, you walk 3 meters from B to A. What's the constant speed, right? What's the average speed over the entire trip? And B, what is her average velocity over the entire trip? What's the average velocity over the entire trip? Right? So the average speed during the time interval is equal to the total distance traveled divided by time. That's the average speed, right? So total distance. Now this is something different. We said it didn't say velocity for the first part of it. Part A is average speed. Again, this is where people will be tricked. Please take a look at the words that are used. Speed and velocity. Speed means distance over time, not displacement over time. Two different things, right? And this is where it's tricky. It's not meant to be tricky. It's like to get you to think about the total distance, the total path length, right? So again, distance from A to B plus the distance from B to A divided by the time AB plus the time of BA, and you get an average speed, where it says 2VAB over VBA, because we don't know the total distance. We have no idea what the total distance is. And they come up with an equation. That's the average speed. Right? They came up with a formula to describe the average speed. Okay? If we were given the distance, if we said the distance is 300 meters, right? And we can figure out the exact number that we want, right? We don't know the distance. We haven't been given that number, so we're going to find the average based on a formula. We're plugging in variables because we have no idea what the actual distance is, okay? And on the other side, when we want to find the displacement, did I copy that again? Yeah, that is A. Yeah, that is A. And B, I'm going to go B again. B is this one. Yeah. And here is where we come up with the average speed of, we plug in the numbers, right? Because we don't know the distance, but we don't need it. Once we start plugging in the average speeds, we get, the average speed is 3.75 meters per second. So first we develop the formula, then we plug in the numbers. Now the average velocity is a totally different thing. Remember, we just saw the same thing. The first thing I saw was velocity. They went there and came back. Who cares what the speed, the rate of speed was? We don't care, right? Because they went there and came back. The average velocity is 0 because they didn't go anywhere, right? Okay. Almost done. A couple more pages, right? And then I'll let you go back to what your regularly scheduled program.
The last slide, the speed is going in one direction and then another.
Yeah.
So would the average that be negative?
Well, because of displacement, it's talking about displacement, right? So that's what they're talking about. And speed is not negative. Speed is total distance. Speed is path length.
So you
Right.
can average negative?
Yeah, no, there's no negative because I'm going there and I'm traveling. As I'm traveling, that's distance, right? Distance is always positive, right? I can't have a negative distance. That's like, how does that work? Even if I travel backwards, I'm still traveling distance. Displacement, I can have a negative displacement that equates to 0, right, or whatever, right? But distance is total path length. That's what I want you to think. That's where people get messed up.
That's why I was asking you.
Yeah.
Negative.
No, negative, but that's displacement, because that's not distance. We're talking about velocities. So when we talk velocities, we talk about displacement. When we talk about speed, we talk about distance. Right? Two different things. Okay, going back to this. Particle moves according to the equation x is equal to 10t squared, where x is in meters and t is in seconds. Okay, this is where Desmos can come into play for you, right? If x is equal to 10t squared, we can assume that, we're going to create a relationship between x and t. Now we have a motion time graph, right? If I have this kind of thing. So let's plug it into Desmos. This is before we do any other calculations. So again, x is equal to 10t squared. So we're going to put 10x squared here. 10x squared, right? So that's what our motion is going to look like, right? Where x is t for time, okay? Do we care about negative values of time? This side, right? We don't really care about this side because these are negative values of time. Time can't be negative for us. We're not time travelers yet, right? And here, well, actually we are, but we're only going in one direction forever, right? But here, that's what the parabolic, that's what the curve looks like, right? So it kind of goes up like this, right? So these are all values of t until infinity. We can start mapping some of these values as we look at some of these places here along the curve. If you actually take Desmos and you drag points across the curve, you can see what some of these values will be, okay, as an example, okay? So that's what the curve looks like. So again, first, conceptualize, visualize what your curve looks like. Second, start thinking about the problem and then what the problem is telling us. So here, back to the mic. So again, here what it says is, now that we have it, where x is in meters and t is in seconds, right? So find the average velocity for the time interval from 2 seconds to 3 seconds. So what am I doing? I'm plugging in values of t, right? That's all I'm doing. So if I take 2 seconds, where x is t, right, or x is related to t, and 2 squared is 4, right? So that means 4 times 10 is 40. So when t is 2, x is 40. That's what it means. So I'm plugging in values of t, right? I'm plugging in values of t, and we're going to get x values. X values meaning the distance, or the displacement, right? So in meters. So that's what that is. So that's 40. And then the interval from 40 to 3 seconds. So 3 times 3 is 9, 9 times 10 is 90. So from 40 to 90, right? So x is in meters, and it says, and what is it asking for? The average velocity. The average velocity. So if I look at it and I go, okay, so from 40 to 90, 40 plus 90 is 130 divided by 2, right? That's the total number but that's over time. So that's the displacement, x final minus x initial, right? Over t final minus t initial. That's going to give you the average velocity, right? And let's see if that's true. Well, we don't have the answer here for this one, but it is. That's how you figure it out. The next one is find the average velocity for the time interval between 2 to 2.1 seconds. Again, it's the same kind of thing. You take the seconds, you plug them in, you get values for distance, and then you kind of do that x final minus x initial over t final minus t initial, or going back to delta, it's delta t, kind of stuff over delta x, or delta x over delta t, x over t meaning velocity, and now you're finding the average velocity. That's another way of finding the average velocity, right? Delta t, the distance or the displacement over time. Changing the displacement over time is your average velocity, and that's what you're doing. You will get questions like this in the test, for sure. All right, last one, or second last one. Find the instantaneous velocity of the particle described in figure P2.1 at the following times. So t is equal to 1 second, t is equal to 3 seconds, t is equal to 4.5 seconds, and t is equal to 7.5 seconds. So how do we find instantaneous velocity? How do we do that? Right, so remember what instantaneous velocity is. It's a tangent to the velocity curve. That's what we want to find, right? So instantaneous velocity for the particle where t is equal to 1. So we look at 1 second across the curve, and what's the instantaneous velocity approximate for that particle? And on the left, you can see the distance in meters that it's traveled, right? That's what this is asking. And the same thing, you have information here for the velocity. Remember, velocity in this case is displacement away from the origin, right? That's what we're looking at here. So the distance away from the origin is that number there. Distance over time, you can find the instantaneous velocity in the same way. Okay, for displacement over time. Okay, so again, these are kind of repeating in some ways, but it's asking the same question over and over again. Okay, here's the next one, and this is the last one we're going to talk about today. Draw motion diagrams, right, for an object moving to the right at constant speed. Okay, how do we draw a motion diagram for an object moving to the right at constant speed? We saw these diagrams last day. I have a car, right, and what would I do? We want to model the car as a particle, right, all the time. We want to model the car as a particle, and we want to draw a motion vector, on top of the particle that's kind of the same length every single time, right? A particle moving to the right at constant speed. That's what I would draw, right? Speed, an object moving to the right at speed up at a constant rate, right? And speeding up at a constant rate. So it's speeding up at a constant rate. So I'm moving to the right and speeding up at a constant rate. Particle, velocity, with an acceleration, that with a vector that's acceleration moving in the same direction, getting larger and larger and larger and larger. That's speeding up at the acceleration is the same, but the velocity keeps on getting larger and larger. You're going to draw the particle farther and farther away. Okay, that's what it's in here. That's number 2. See, an object moving to the right is slowing down at a constant rate. That's where the acceleration is in the opposite direction. Velocity is going in one direction, acceleration is going in the other direction, and those two vectors are going to affect each other. So you draw it like this. You say, okay, so I start off, the car is quite separated, and then what's going to happen is it's going to make the car or the particles going to get closer and closer and closer together at the end, right? Because it's going to continue to slow down, just like we saw in the car example we had from the vectors going in opposite directions. Okay? So that's that one. An object moving to the left and speeding up at a constant rate, an object moving to the left and slowing down at a constant rate. And how would your drawings change if the changes in speed were not uniform? That is, if the speed were not changing at a constant rate. That's challenging, right? Because we've been always dealing with a constant rate of speed, right? So you have to show fluctuations in your acceleration or fluctuations in your velocity. So larger and smaller vectors, That's what you're showing. So all the stuff that we've talked about so far in motion in one direction, there's really a couple things we talked about. We talked about some basic kinematic equations. I want to just review these before you go. And I also want to talk about the assignment. Okay, so the assignment was supposed to be released last week. However, I know I was speaking to Joss about it, and I said, you know, I'm not sure that I want to release it yet. And the reason for this is because we don't have all the information. In previous iterations of this course, we would do motion in one direction first, then I would release the assignment, right? Because there's going to be questions about motion in one direction and also graphing in the assignment, and you wouldn't have had any of the information until today, right? So that wouldn't get you to start properly with that. And I wanted just to talk about the motion, the stuff that just to review from last week that we talked about. We talked about average velocity, how to figure this out, right? That's what I was saying here. This is the average velocity. It's another way to find it. And the difference between average velocity and speed. I'm also going to, this is the idea of the difference between distance and displacement, where we just have to draw a line between the start and end. And then we're starting to get into the kinematic equations that we talked about before. So these kinematic equations, there's the stuff I was just talking about with your drawing, the drawings of your cars or your velocity and so on. But you want to start thinking about these kinematic equations. So here's one of them. Here's the first one, right, that we talked about, right? So number one is velocity in the x-axis final is equal to velocity in the x-axis initial plus axt. That's the one that we would use in many cases for acceleration. You need to know these equations, okay? But again, let me talk about this again. I'm going to give you a cheat sheet. So even though you need to know the equations, it's not for you to remember the equations. It's you need to know when to use these equations. How do you apply these things, right? You can't just like spray and pray for this one. You got to test it out and make sure that it kind of happens the way you think it's going to happen, right? This is the second one where we want to find the average velocity, and then that's another way of finding the average velocity, right? The first way was, remember, we kind of take the x final minus x initial, and then t final minus t initial. That's the other way. There's two ways to find the average velocity, right? With or without time, okay? And this is the big one. This is the one that I want you guys to remember. If you can remember anything, and actually we did this in a different form of this in AI last semester. When we were doing our motion, we were doing our seat algorithm, right? We used this equation actually, right? We used the kinematic equation. If you actually look in your assignment framework, we actually wrote it out. We said this is the kinematic equation, and we wrote out this exact thing, right? So again, this can apply. This is kind of a key equation for us for jumping in a platformer, sending a bullet into space, the whole thing. Throwing a grenade, this is the same equation right here for your, for the stuff we're doing. Why? Because if we just remove x, you don't care about x. It's the total position. So we look at a position or a transform, right? If I'm looking at a position for both x and y, right? Then I have the position deltas from the initial position to the final position. That's what we care about. And this, in this case, is just on the x-axis. Next week, when we come into play with this, we're going to see that this is going to be motion in two directions. We're going to extend our model, right? And we're going to start talking about the same equations, but in 2 dimensions instead of 1. Questions around this stuff? I know this is not the most exciting lecture today, but you need to see this stuff because it's going to come up on a test. This is just basically the foundations for all the motion that we're going to be doing this entire semester. No, you're shaking your head. Does that mean you're bored out of your mind? No? Yes? Yeah, you're bored. All right. I know we can talk about. I'd rather talk about cyberpunk too. I'll be honest, right? But it is what it is. We have to get through this. And again, I don't think this is negative. I think although we're probably getting some of this through osmosis. When you start coding, you're like, I tend to remember something that Tom said or Josh said. Oh yeah, they mentioned this, and then it's going to click. You can't click it right now because you're not coding, right? When you start doing your coding, this is going to make more sense. Okay, guys? That's it for me, guys. Thank you so much. Look for your assignment this week for sure. It's going to come up. All right. If you haven't partnered with anybody, the assignment is not a single assignment. You're supposed to partner with this one, right? So please make sure you join the teams up on Blackboard. Okay. Thank you.
Yeah.